Okay, it's recording. Okay, let me start presenting. Okay, I hope you can all see. If you cannot, please interrupt me. Okay. So today we start speaking about server-side security, okay? So we spent a lot of time working on the client side, and we started the reasoning about the security of TLS, so the transport layer, essentially between the client and the server, and we eventually reached the server. So we start discussing for the next lecture about server-side security issues. In this lecture, in particular, we will focus on 3 classes of problem. During the next lecture, we will see 3 more classes. But for now, we discuss on the following problems. First problem is access control issues. We already mentioned about these problems at the very beginning of the course, but we will go a little bit more in detail in this lecture. So we'll discuss in particular about the incorrect adoption of the authentication and authorization mechanism on the server side and how they can be abused by the attacker. We will then discuss about code execution issues. Of course, these are very dangerous attacks because essentially there are bugs in the application logic which allow the attacker to execute arbitrary code. And finally, we will start discussing about file security issues. Okay, so since the web application is hosted on the server and the server is sitting on top of an operating system, there might be some dangerous interaction between the web app and the file system. There is, of course, the king of server-side vulnerabilities, which is SQL injection, but we will not discuss SQL injection on server-side and database security in this part of the course, since this was already covered in the first module. But keep in mind that, of course, SQL injection is a prominent problem for server-side security, so be prepared about that as well. Okay, let's start having a look into access control issues. And in particular, access control vulnerabilities are dangerous because they enable privilege escalation. What is privilege escalation? Is the ability for the attacker to get undue access right, essentially. It is useful to have a classification of privilege escalation to understand exactly what is the impact of this kind of access control vulnerabilities. We have vertical privilege escalation. In this case, the attacker is able to get access to data and functionality of users who are strictly more powerful than the attacker. For instance, the attacker is able to abuse some functionality which is intended to be used only by system administrator, although the attacker is just a standard user of the system. We have horizontal privilege escalation, which is a case where the attacker is not becoming strictly more powerful according to some hierarchy of roles, for instance, but it gets access to data and functionality which is given to users who are just as powerful as the attacker but have a different identity. For instance, this is the case where you have the attacker being able to impersonate another customer of the system. So of course, this is not as dangerous as vertical privilege escalation because the attacker is not getting, for instance, administrative rights. But this is still dangerous, of course, because the attacker still gets access to something which is unintended. And finally, we have the context-aware privilege escalation, which means that the attacker is able to access data and functionality which is normally available only in a web application state which is different from the current one, like a different time, a different geographical area, or if you want to think about workflows, the attacker was able to bypass some security checks which were supposed to happen in the past compared to the present point in time. How can we introduce access control flows in web application? We will discuss several examples. Let's start from one example which is particularly dangerous. In this example, we consider the case where we supply some security critical functionality through links which are available only on the admin profile and not in standard user profiles. You can see an example here. So this is essentially a link for the delete functionality, where you are sending a GET request to the delete interface, which is, of course, restricted to the administration, and you pass the user alias as a parameter. What's the problem here? The problem here is that although this link is only available to the administrator, nothing prevents the attacker from sending a GET request directly to this endpoint to force the deletion of the user. Okay, so just hiding the link inside a private area which is not accessible to anyone else is not a robust solution, because the attacker can completely bypass the user interface and do essentially whatever he likes by forging HTTP traffic. Let's discuss a couple of wrong solutions, or at very least suboptimal solution to the issue. One possible solution is including some secret inside the URL. Of course, you might extend this GET request, including some secret which is only supposed to be known by the administrator. This is plausible, but notice that this is still not optimal, because the attacker might still be able to guess or brute force the secret. Or even worse, you might have some other flow in the application, say an XSS, which will enable the attacker to get access to the secret. And so this is essentially a bypass, which will make the attack possible. So this is still not the best you can do. Also, the secret might be leaked in other parts of the web application. So even if you don't have XSS, it might be possible that you are accidentally leaking the secret for some other reason. Because, for instance, it might be that you are including some information in the robots.txt file, where the attacker might be able to disclose a bunch of URLs which are supposed to be secret, just because you want crawlers to avoid the navigation of these URLs. So be aware that including secrets in the URL is not the best solution. We will discuss the best solution after checking other possible problems, but this is not great. Let's consider other cases where access control is flawed in web application. This is a very common vulnerability, or at very least used to be common back in the days. Now with better web development framework, this is not so common anymore. But the key idea is implementing a sort of parameter-based access control. So the idea of parameter-based access control is that you implement access control by means of HTTP parameter. For instance, parameter which contain the role of the authenticated user. It is clear that this is not a great solution, because if you just rely on this parameter, you are essentially not protecting your web application, because the attacker could just change the parameter freely. Okay, and this generalizes to all the cases where you store authorization information on the client side. For instance, you store this information inside a cookie, or you store this information inside a web storage. So every time you put authorization information directly into the client, you cannot trust this information. Okay, this is not a robust solution. Another prominent vulnerability which received a lot of attention because it was included by OWASP in the most dangerous vulnerabilities in the wild for a few years is so-called insecure direct object references. This is, again, something along the same lines of the access control flows we discussed. And the key idea is that the web application is making use of some user-supplied input to directly access objects. What do we mean by objects in this context? We mean something like files, database records, etc. So if you want to have an example, let's assume here that we have this URL, foo.com/account/12144.txt. This might be, for instance, some code which was generated for you, and maybe can contain information like your medical health record. And of course, having something like this embedded directly into the web application is not great, because you might, for instance, think that this is some sort of incremental sequence number which is indexing all the possible health record of the other patient. So you might try to access 12145, 12146, etc. And eventually, you might be able to hit some medical record which was given to some other user of the system. So this is an example of horizontal privilege escalation, where you have a file which is intended for you, and you have a code which grants access to this file, but you can try essentially to enumerate all the codes to get access to other files which are intended to be supplied to other users of the system, like other patients in this case. So in general, embedding this kind of direct reference to information is not great from a security perspective, exactly for this reason. Other variants on the topic include method-based access control. The idea of method-based access control is that you make, this is not really, let's say, a design pattern, it's more like a sort of overlooked vulnerability. And the idea is you perform some access control checks only on some HTTP method. Something like, okay, I will inspect that the user is authorized when I get a post request to this endpoint. But since the backend was configured differently from what you thought, it is also possible that the same endpoint also accepts other HTTP methods like GET, and in that case, you're not performing any authorization check. Okay. It is interesting because if you have experience, for instance, with developing web applications using Flask, Flask by default allows only GET methods everywhere. And if you want to relax from GET, you have to explicitly pass a set of available methods like post, GET, whatever you like. And so you have full control of all the methods which are eventually accepted by the web server. But of course, details vary across different web development frameworks. So be aware that you might implement some checks over a method and forget to implement the same checks over another method. And the last point of, last kind of flow I want to mention is related to multi-step processes. So this is a great example of context-aware privilege escalation. In general, you might have sort of a transaction with multiple steps, and you might implement some security checks at some point of the transaction, but you don't redo the same checks later on. If you implement something like this might be a problem. To exemplify, let's consider this case. In this case, there is a link which contains a request to delete a user, which is passed as a parameter, and we also pass a Boolean confirmed, which eventually says that we already implemented some checks, because since the delete is a dangerous operation, we ask explicitly for confirmation, okay? So the protocol will be something like, okay, I will ask to delete Alice, and confirm will be false. Then the server will warn me that this is something which is dangerous, and for instance, the server might even force me to authenticate again, because indeed this is a security critical functionality, so the server really wants to be sure that I really want to do that, and this is my own identity. And after confirming, we send a second request to the same endpoint, but we switch the Boolean parameter from false to true. If we do something like this is not sufficient for security, because the attacker could try to completely bypass the first two checks, first two steps, and send directly a message which include user Alice and confirm equal to true. And in this case, the attacker will be able to completely bypass the security checks. And this is an example of context-aware privilege escalation. So the attacker is not working necessarily outside of this capability, but it is bypassing some security checks. So let's come now to how we can prevent these access control vulnerabilities. We already mentioned a little bit about these advices, but it's better to recap them and maybe expand upon them. So the first advice, of course, is to mistrust the client. We said this multiple times, but everything which is on the client cannot be trusted because the user of the client might be malicious. So whatever comes from the client might be tampered by the attacker. So if you store secret data, the attacker might be able to get access to it. If you store, let's say, data whose integrity is important, the attacker might be able to tamper with that data and compromise the integrity. So never trust the client for access control checks. Second point, which is very important, and it's sometimes underestimated in the wild, is never rely on obfuscation alone for access control. So it means essentially that you cannot protect your data just by relying on secrets. Using secrets is good, because if you use secrets, and you might make some attacks harder to carry out, and most importantly, you might make harder for the attacker to guess the application logic, and so you are essentially giving less weapons to the attacker to try to attack you. But as you probably know from the first model of security, just hiding information is not great. So we can do better than hiding information. Hiding information is a useful mitigation because you make the life of the attacker harder in general, but you cannot rely on obfuscation alone if you really want to have a good degree of security. Point 3 is the most important, in my opinion. So this is the right way to prevent access control vulnerability, which is always perform authentication authorization, implementing a deny by default policy. So what I mean is that every time you process an HTTP request, the first thing you have to do is checking the cookies inside this request, checking whether these cookies indeed identify a valid session. So you implement authentication. And after that, since you know the user identity, you can implement an authorization checks. So for instance, in the case of the medical record example we discussed, it's great if you make the name of the record harder to predict for the attacker, because this is essentially hiding information for the attacker. But it is even most important if you actually check that the user who asks to download a file is intended authorized to access that file. This is, of course, the best solution against this kind of vulnerabilities. Other points, which are sometimes overlooked, is that it is better to use a single application-wide mechanism for access control. We will see other examples in this lecture, because one problem with server-side security is that sometimes server-side security is building on top of many different technologies. Client-side security, in a sense, is simpler, because when you develop the client-side logic of your web application, most of the time you are using JavaScript. JavaScript is not a good programming language, as you are probably aware of, but nevertheless, it is just one language. In the case of servers, you might use many different technologies, like a mixture of PHP and Python to implement the same web application. And if you use different frameworks for access control, that might hide a problem, because it might mean that you have two different access control systems which make slightly different assumptions, and you might even try to make the two go together, but this is very error prone. So in general, if you can implement a single application-wide mechanism for access control, for instance, on top of the front-end server, that's definitely a better solution than relying on multiple access control systems. Other last two recommendations is keep track of state information along multi-step processes. This is not something which is esoteric. You can easily do it by keeping track of information along the session. So in the case of the workflow example we mentioned, where you explicitly ask for confirmation, it's much better to check for this confirmation based on server-side information rather than by checking the HTTP parameter, which can be tampered by the attacker. So you have session information, just use it. Store session information to keep track of all the state of this multi-step process which we mentioned. Last recommendation, in the case of very critical action, it's much better to force authentication. Authentication is annoying to users because this is something which goes against usability, right? But nevertheless, if the user asks for something which is really security critical, it's probably better if you ask for authentication again. This is another layer of security which can really make a difference for irreversible action like deletion of user, etc. Let me take a glass of water. We'll be right back. Okay, do you have questions so far? Okay, if you don't have questions, let's move to the second class of vulnerability, which I want to mention in this lecture. This is an interesting and very well-known web security vulnerability, which is called path traversal. I don't know if any of you is already familiar with this, but the idea of path traversal is that the attacker is essentially able to read arbitrary files from your server by abusing the fact that you don't implement appropriate checks over file names. To understand how path traversal works, let's consider a very simple example. So let's assume we have a web application which loads images. And the key idea is that this web application is loading images by making use of a file name parameter. So for instance, in this case, you are sending an HTTP request to the load image endpoint, and you pass one identifier 218.png as a parameter. And what the web application will do is fetching this image 218.png and put the image inside the HTML, and the image will be rendered. Notice that this file name parameter is making use of a relative part. For instance, we can assume that this part is starting from the base directory of images, say that this directory is var // images. Okay, so when you ask for this inclusion, you will fetch var // images / 218.png, and you will embed this image inside the HTML. What the attacker can do is abusing of this functionality to try to access the password file rather than an image. And the idea is the following. The attacker crafts an HTTP request, which is sent to the same endpoint of load image, but the file name parameter will have a much different format than what is expected. For instance, in this case, the attacker will send // etc/password. So for any of you who are familiar with Linux, I guess most of you, you know that by using this syntax, you can essentially go on top of one layer in the file system hierarchy. So by doing this, you will move out of the images directory and you move into var // and by doing this, you will just move inside var. And with the third one, you will move on the root of the file system, and from there you might eventually walk into etc/password. Of course, you can try to abuse a functionality without necessarily using an image tag. Just send an HTTP request to this guy, and if the server does not implement protection against path traversal, you will get the etc password file directly into the HTTP response. So what is interesting about path traversal, it is a very easy vulnerability to explain to my eyes, but it's not obvious how to fix it. In the next slide, I have included some examples of wrong attempts to deal with path traversal. So we might consider different options. Let's start from the first one. In the first option, we start from the idea that the problem in that case was that we were using relative path. So since we're using relative path, the attacker could try to use this // trick to walk through the file system. If we just say, okay, the problem is with relative path, we can just use absolute path everywhere, the problem, of course, is not solved. The only difference is that the attack payload will be different from what we had. What the attacker will do is just trying to access the etc password file directly. So maybe this solution was a little bit naive. So let's say, okay, maybe we can live with relative path. We're not so bad after all. We will implement some form of sanitization over the content of the HTTP parameter. And so, for instance, we might try to strip away the nasty // sequence. If we do it, however, it might still be possible to attack the web application. To understand why, let's have a look at this attack payload. In this attack payload, if you try to strip away all the occurrences of // what you do is you remove this free character here, these free characters here, and these free characters here. So if you remove this character, you get exactly the dangerous sequence which we had in the previous slide. So by pruning away this nasty sequence of characters, you eventually get the attack payload which was creating troubles in the previous slide. So of course, if you just strip away this sequence, this is not sufficient. So what you have to do is to implement this stripping recursively to ensure that you remove all the sequences which also occur after stripping other sequences, right? So let's assume we make even this strip recursive, and let's assume that this is easy to do. What the attacker could try to do is trying to fool us by hiding the presence of the sequence which is creating trouble to us. So for instance, rather than attacking through ... it might try to attack us through the URL-encoded variant of the dangerous sequence. So in this case, we're using %2e to represent the dot. And so we are hiding ... as %2e /. So essentially, by URL encoding the same attack payload, we can even try to prevent any form of sanitization by stripping this kind of sequence. So of course, if you really want to have security, you also have to URL code everything well in advance, multiple times, to ensure that indeed the attacker is not performing multiple encodings of the same attack payload, strip away all this stuff recursively, and as you can imagine, this is not a trivial task. Okay, so I think I'm trying to convince you and driving you into thinking that it's better if you don't implement these kind of things yourself. So let's assume these solutions are not great. Okay, I think I convinced you. Let's consider other possible solutions, and let's see that also these other possible solutions are not very robust. Let's try out different approaches. So let's assume that rather than trying to sanitize the parameter by removing all the sequences which look nasty to me, I will try to enforce some sort of well-formation condition on top of the parameter. And for instance, a possible idea is that we require the HTTP parameter to start with the base directory of images. So in this case, since we don't want to navigate away from var www.images, I might force the HTTP parameter to start with /var/www/images. This is not sufficient. You can see an attack here, where essentially you are using this information here to navigate away from the intended path. So this path has 3 layers, 1, 2, and 3, but these layers are eventually removed, 1, 2, and 3. And so after this part of the path, you are back into the root of the file hierarchy, and you are eventually able to access etc password again. Okay, so maybe this is not what we wanted to do. So what we can try to do is that since we work with images, we might require the HTTP parameter to end with the right extension. So if we force the HTTP parameter to end with .png, for instance, we rule out attacks where the attacker tries to get access to the password file. However, there are some language-specific bypasses. I show you one bypass here for the PHP language, and this is called the null byte attack. In the null byte attack, what we do is that we put a null byte, which is %00 at the end of the name of the password file, and then we put .png at the end of the parameter name. In this case, if you just look blindly into this parameter name, the parameter name will look okay, because this parameter name is terminating with .png. However, what PHP will do is throwing away everything which comes after the null byte. So as a matter of fact, although this guy looks like an image file, it is not actually an image file, because PHP will still try to access etc password. Okay, and there exist other language-specific bypasses, which I'm not going to discuss. But I think that I convince you in this couple of slides that sanitizing HTTP parameter to prevent path traversal is something which is extremely complicated. Also, I want to make you appreciate that this kind of attack is dependent on the underlying operating system. All these attacks which I presented you assume the use of the Linux operating system. But if rather than using Linux, you use Windows, you have other ways to access the file system. And so it means, in particular, that the kind of sanitization recipes you have to put in place will be different from these ones. So in general, sanitizing and checking condition about the HTTP parameter is not a great solution for this kind of attacks. So what is a great solution? The great solution, as most of the time when we have this kind of injection vulnerabilities, is to not do it by yourself. But before discussing the solution, we will analyze another dangerous case of path traversal. Path traversal is typically presented as an attack against confidentiality. Most of the time, people consider this instantiation of the attack where the attacker is getting access to the password file. And this is a very convincing argument to show you why path traversal is dangerous. However, it's also important to notice that path traversal is also an attack which can break integrity. And can break integrity in a very bad way. To explain you this example, let's consider a file upload interface in PHP. So this is a very simple snippet of PHP, which is supporting file uploading. And the key idea here is that when you upload something using PHP, you use a files variable which contains a bunch of information. Okay, so let's see in particular how the PHP works. So we define a variable uploaded, which is just let's say a convenience to avoid referencing to file subfile all the time. So it's just a shortcut. What we do is we first create the destination directory for the uploaded file using the sprintf function. So we want to put this inside the uploads directory, and we want to give the name which was supplied by the client. So the name parameter of the dictionary here is the name which was supplied by the client through the client file system. Okay. So if I want to upload a file which is called banana.txt, the file the name banana.txt will be bound to uploaded name. Then we call move uploaded file to pick the content of uploaded temp name and put it inside the destination directory. Temp name is a temporary name which is created by the web server when you upload banana.txt over the web server. Okay. So in this case, what we do is we pick a file with a temporary name and we put it inside the upload directory with the original name of the client file. So if the attacker wants to attack us, what the attacker can do is crafting a file whose name is ./index.php. If the attacker is able to upload this file, the attacker is actually able to take control of the web application logic by overwriting the real index.php file of the web application. So the attacker can essentially get a web shell on the server, so it can get arbitrary scripting capability on the server side by crafting appropriate logic inside index.php, thus prepending // to the PHP file name and uploading this file over the web server. Okay, so path traversal is not necessarily a problem of confidentiality. It can also be a problem of integrity, especially when we have application which support some file uploading interface. We will discuss other cases where file uploading is dangerous in the rest of the lecture, but for now, keep in mind that path traversal is also dangerous for integrity. So of course, it's better to fix this guy. And how do we fix it? As we said, key rule is don't do it by yourself. In general, trying to filter out all the possible ways for the attacker to play with the file names is just too complicated. So the most common solution against path traversal is to leverage some existing API to canonicalize the file name. What do we mean by canonicalizing the file name? We mean that we pick the file name and we resolve it in a unique way inside an absolute path. If you really want to have an example about this, let's consider this case. In this case, we have a very weird representation of a valid path toward the etc password file. If we canonicalize this, what we get is just /etc/password. Okay. Of course, canonization routine might be complicated. It is, of course, very dependent on the underlying operating system. But at the same time, it's also true that many web programming languages APIs provide native functionality for canonicalizing file names. So just build on top of this functionality. Once you have a canonical representation of the file name, you can implement the security checks you want over such canonical representation, which is much easier to deal with. And for instance, you might check that the canonicalized file name starts with the expected base directory. And this is very easy to do. In this slide, I put you an example for the Java programming language. So in the Java programming language, you can use the getCanonicalPath method. And this method, with just this simple call, you canonicalize the file name of the file. And then you can use, for instance, the start with method to check whether the canonicalized file name indeed is starting with the expected base directory. If this is the case, you process the file, otherwise you throw an exception and you make your program fail. Of course, you have very similar abstractions also for languages like Python, PHP, and etc. So my advice is read your documentation of the web development framework to find the right methods to do this task and just rely on top of that. It's much easier and much more robust than doing it yourself. Clear so far about path traversal? Do you have any question? Okay, so if you don't have questions, let's move to another class of vulnerabilities. Also, the other class of vulnerability is a server-side security vulnerability, and this is called command injection. This is a very nasty vulnerability, and this is nasty because it essentially allows the attacker to execute arbitrary commands of the underlying operating system on the server. Most of the time, this kind of vulnerability is enabled by the fact that you build on top of some legacy functionality which was implemented, for instance, like a bash script or a Perl script, and you just call this kind of functionality from your web application. To understand with a concrete example, let's assume we have a web application which offers access to stock information. Okay, so we have this foo application which has a stock endpoint, and we can provide two parameters, the product ID and the store ID. And the response of this guy will be the number of items with product ID 381, which are still stored inside the store with ID 29. To retrieve this information, the web application is not relying on internal logic, but it's calling an external script. For instance, for legacy reason, this application might call a stockreport.pl file, which is a Perl script, and it is essentially passing the two parameters it got from the HTTP request directly to the script file. What's the problem here? It's again an injection problem if you think carefully, because the two parameters product ID and store ID are just read from the HTTP traffic and put inside the call to the operating system. So the attacker can try to get access to some sensitive information, like the current user identity, just by trying to put some dangerous payload, for instance, concatenated to this information like 29. You can see an attack payload here, where the attacker sends a product ID 381, like in a legitimate use of the web application, but rather than passing just a number as a store ID, the attacker passes 29% free B. What is this guy? Is a semicolon. And then whoami with a valid Linux command. So what's happening in the backend is that the backend will be calling stockreport.pl 308129 semicolon whoami. The semicolon in bash is a separator which executes two commands one after the other. So the end result is that rather than calling a single command, stockreport.pl, with the right parameters, the backend will call two commands, the stock report and the whoami command. And the results of this command will be returned back to the client. So by doing that, you're able to retrieve the information which is returned by whoami rather than the information which is returned by stock report. And you're essentially getting scripting capability on the operating system layer of the clients, of the server side, which of course is very, very dangerous. There are a bunch of attacks you can try to mount. I provide you some insights here. So these are some advices of ways you might try to find command injection vulnerabilities. Again, command injection is something which is really dependent on the underlying operating system. So if you want to implement command injection on Windows, of course, it's different from implementing command injection on Linux. I show you some example of important bits for attacks against Linux, but the intuition generalizes to Windows as well. For the details will be different. So in the case of Linux, interesting commands to run on the server might be whoami, to understand who is the user I'm interacting with. For instance, if the user is root, I know that this user is super powerful. So I might try, for instance, to remove critical files from the server, since I know that I have root access to the machine. uname-a is giving me back the version of the kernel. So I might try to get, for instance, information about the system to know that the system is building on top of a legacy Linux kernel with some known vulnerability, and then I can try to exploit this vulnerability to get root access to the machine. Other useful commands include the ps command. The ps command is the command you typically use on Linux to get the list of the active processes. So by using the ps command, for instance, you might get access of important information, which is telling you which services are running on the system. And once you know which services are running on the system, you might try to Google for some vulnerability which is affecting a specific version of these services, and you might try to exploit this vulnerability to get access to the machine. wget instead is a service to retrieve files, or better, to send HTTP requests and collect the corresponding HTTP responses. And by using wget, you might try, for instance, to download some malware from your own server, and then if you find a way to execute the malware, of course, you get access to the machine. These are the commands we would like to use most of the time for command injection. There are others which depend on the specific attack scenario, but this is just to give you a flavor. If you want to inject this command, we need to rely on separators, because in the command injection attack, like in the previous slide, you're abusing some command and you try to essentially concatenate it to some other command. And you have many different ways in Bash, for instance, to concatenate different commands. In the previous slide, we mentioned the semicolon operator. And in semicolon operator, the meaning is essentially to execute the two commands one after the other, no matter what. But we have also other meta characters which might be dangerous for you. Why I'm mentioning many different meta characters? Because I want to give you the idea that preventing this kind of attacks is complicated. Because it means that you have a very strong understanding of the Bash shell, for instance, in this case, and you're able to understand all the possible characters which might enable attacks. This is just essentially a way to telling you that filtering out all these dangerous characters is complicated. I very quickly mention this other example. So you have the ampersand command, which is essentially used to run a command in the background. So by putting an ampersand between two commands, you put the first command in the background and you execute the second one. Then you have the pipe, and the pipe is a way to concatenate two commands such that the output of the first command becomes the input of the second command. And then we have this logical operator like the double ampersands and the double pipe, which are a way to conditionally execute the second command depending on the results of the first command. So these are all useful meta characters which you might try to abuse to mount command injection attacks on existing servers. Of course, don't do it on real servers, it's just for teaching. But be aware that you have many different combinations, and your expertise with the Bash shell and the Linux system is essentially an expertise which reflects in your capability of performing command injection attacks. An important point which I want to mention is that most of the command injection vulnerabilities are so-called blind. I think we already discussed about blindness when we discussed SQL injection. And the key idea of the blinded exploitation of vulnerability is that most of the time it is not obvious whether the command you injected is a command which is indeed executed by the system. Why is that? Because in the case of command injection, you are essentially calling some operating system command. And the output of this command might not be immediately visible to you. For instance, the command might write to some local file which is not accessible to you, or might take some, might put some output on the screen which is not visible to you. So to exploit this command injection vulnerability, sometimes you're forced to play blind. And when you're forced to play blind, the best way you can act is by trying to exploit some side channel to identify whether command injection was successful or not. Because if you don't have this signal, you don't know whether you're actually managing to make the server execute some command or you're not able to do so. I mentioned here 3 prominent examples of side channels which are useful to execute, to learn information about the execution of the command. I noticed a typo in this slide. So here we are using, for instance, the command ping, which is a way to, you know about ping, it's a way to send a ping packet to a server and get the response back. In this case, you can abuse the ping command to send a request to the localhost. And by using the -c option, you can actually force the ping operation to go on for a fixed amount of time. So in this case, I forgot to write in the slide the parameter. The parameter should be ping -c, say 10, 127.0.0.1. And the meaning of this is try to ping the localhost interface for 10 seconds. So what you know is that if the HTTP response is taking a lot of time to move back, it means that very likely command injection was successful because you forced the server to wait for 10 seconds before replying back to you. Other side channels include output redirection. For instance, the whoami command is displaying some content on the console, and you might not get this information back. So what you can try to do is to actually redirect, and you can use the greater sign to redirect the output over some public file which is accessible to you. So you can run the whoami command and redirect the content inside /var/www/static/whoami.txt. And what you do then is from your browser, you try to access this publicly available file. And if this file contains some content and is present, it means that the injection was successful. Other possible tricks involve a domain resolution. So since domain resolution to attacker.com is handled by the attacker, what you can try to do is forcing the DNS lookup of an attacker-controlled subdomain like canary.attacker.com, so that by looking into the log of the DNS server, you're able to understand whether an HTTP request was actually fired. And something which I want to mention is that you can also leverage some other facilities of Bash, like the backticks. I don't know if you're familiar with the backticks, but the idea of backticks is essentially similar to what you have with the $ syntax in Bash. They give you a way to evaluate a command on the fly. For instance, you can see an example here when we exploit domain resolution to exfiltrate a secret. What we do is we call DNS lookup over a subdomain of attacker.com, and the name of the subdomain is what you get by executing the whoami command. So just by looking into the DNS log, you might find out who is the user of the system who is affected by the common injection vulnerability you are exploiting. Of course, you can use a combination of all these techniques. What I want to mention is that in general, common injection is not an obvious vulnerability to exploit. Most of the time, you're forced to play blind, and you have to take advantage of some side channels to know whether your attempts are working or not, essentially. How do we fix it? The simplest way to defend against command injection, and it's also the recommended way, is to avoid calls to the external operating system commands. In the previous example, we called a Perl script to collect some data. My point is that most of the time, you don't really need to call some external command. You can just use some application level library for the same task. This is way less dangerous because it doesn't give you a way to script arbitrarily operating system commands. If it is not really possible to call application level libraries for the task, which is still unlikely, you can try to deal with this command injection attack by sanitizing your input. Again, the key idea is that you are not supposed to do it by yourself. I hope I convince you with the path traversal example, but command injection has exactly the same problem because you have tons of commands which are particularly dangerous, and you have meta characters which are different and variegated, which can be trying to be used to chain different commands together. So if you want to sanitize your input, please do that by using existing libraries. For instance, you can use the shlex.quote function in Python, which is a way to escape all the shell commands and meta characters from a Python input. Python also gives you other ways to solve command injection vulnerabilities. In particular, you can use subprocess.call method in Python. And this is a very neat method because the key idea is that by calling this method, you are supplying first the command and then the parameter. So essentially, the intuition is very similar to what you have when you use prepare statement to prevent a SQL injection. In a prepare statement, you fix the structure of the SQL query and you leave some holes which are supposed to be filled by parameters. When you use subprocess.call, the key idea is essentially the same. You fix the structure of the command you want to execute, and you just leave some holes to be filled by the HTTP parameter. And so all the holes which will be filled will be interpreted as literals rather than as command. Of course, these examples are based on Python, but you can find very similar functionality for most other programming languages. So again, the key to prevent this kind of vulnerability is to be aware about the details of your system and don't invent anything, but just use most of the libraries which are already available. Let me take some more water. I will be right back. Okay, questions? Of course, you can check the documentation of this library to get more insight, but I hope I give you the flavor. So the flavor is either sanitize or separate command from parameters. These are very common tasks. But the most important and prominent way to solve this issue is don't call operating system command. Any question about this? Okay. So let's move into another class of vulnerabilities. All these kind of vulnerabilities are somewhat related. So you will see that there are connections between them while retrospectively checking the slides. So don't be afraid by the fact that I'm mentioning many vulnerabilities. because the key idea underlying many of these vulnerabilities is actually the same. So we discuss now file inclusion vulnerability. File inclusion vulnerability happens when we have a web application which includes server-side code without appropriate sanitization. So again, it's a problem about injection. And the problem of inclusion is a problem which is most notable in the context of PHP, but other languages like JSP are vulnerable as well. So this is not a vulnerability which is shared by all programming languages, because we have some programming languages which are better disciplined and don't have dangerous facility like file inclusion. But still the problem is prominent because PHP is vulnerable and JSP is vulnerable as well. To exemplify, let's consider this very simple snippet of PHP code. In this snippet, we check whether the GET request is bearing a page parameter. If this is true, what we do is we call the include command, and we pick the content of the parameter, we concatenate it to the PHP, and we fetch that PHP file, and we execute it directly. It is very intuitive that this is a potential security problem. Because if the attacker was able to pick some attacker-controlled PHP code, the attacker could force us to execute this code in the application origin. Let's consider some examples. So let's start from the regular usage, and then we will discuss a little more in detail about malicious usage. In a regular usage, we will have a request to foo.com. We call the endpoint index.php, and we pass as a parameter page containing contacts.php. The result of this request is that what we see on screen is the page index.php, but the content of the page is fetched from contacts.php. This is the regular usage. Of course, there are many ways to try to abuse of this functionality. And we discuss 4 possible examples here. First example of malicious usage is a denial of service attack. By passing the index.php page itself to the parameter, we're essentially forcing a recursive inclusion of the same page over and over again. So the result is that the web server will be killed by all these self-recursive inclusions, and you have a denial of service vulnerability. Other attacks are called remote file inclusion and local file inclusion. The vulnerability is actually really the same. The key difference is where the content which is injected by the attacker is fetched. In the case of a remote file inclusion, what's happening is that the attacker is fetching some content, like a web shell, from the attacker control domain. So in this case, by passing this argument will be passed as a parameter of the include function of PHP. And the include function of PHP does allow the specification of arbitrary URLs. So by sending this parameter, what happens is that the content of shell.php, which is hosted by the attacker, will be taken and execute inside the origin of foo.com. Of course, this is a major problem for both server-side security and client-side security. So you can try to use this shell either to steal client-side information from the page, because this shell will execute in the foo.com origin, or you can try to use this vulnerability to attack the server directly, because you can execute arbitrary PHP code inside that. In a local file inclusion vulnerability, the attack payload is not fetched from the attacker server, but it is fetched from some local file on the foo.com server. This is very easy to exploit, for instance, when the server has access to some upload functionality. So for instance, what the attacker can do is try to upload some shellcode file on the web application and inject this shell file inside foo.com as follows. So for now, we discussed essentially denial service and integrity vulnerabilities. We also have confidentiality vulnerabilities, because by including stuff, you can include indeed any arbitrary content from the server. So if you pass as a parameter //etc/password, you are essentially forcing the server to include the content of the password file inside the page and returning the page back to you. In this case, notice that we are combining essentially a path traversal vulnerability with a file inclusion vulnerability. So all these attacks go essentially hand by hand. We will discuss also about the problem with file upload. We already anticipated something about that. But as you can see, all these kind of vulnerabilities are somewhat interconnected. It's worth noticing that current PHP configuration, I don't recall from this version, I think version 5, prevent remote file inclusion by default. So in this kind of attack, so here, will not work. So in most PHP version, modern version, you cannot try to implement something like this because this is not working again, but you can still try to attack by using local file inclusion, denial of service, or to force the server into exfiltrating data. How do we fix it? Again, the idea is not much different from what we discussed in the previous slide. The key idea and the key important bit here is that most of the time, it's not hard to keep track of a whitelist of allowed resources for inclusion. File inclusion is a dangerous functionality. So it's a functionality that you should use sparingly, which means that the number of included content should be very, very limited. Say 3, 4, 5, 10 files. If these are the numbers, you can keep a whitelist of such file, and you only include content which is fetched from these files. It is worth noticing that you can combine this defense technique with the canonicalization approach we discussed for path traversal. In particular, file inclusion vulnerabilities can try to exploit path traversal vulnerabilities as well. So the key idea, again, is to sanitize the input by using some API which provides a canonical representation of the file name. A reasonable approach in this case is that we enforce a base directory for file inclusion after performing canonicalization. This works reasonably well for most practical applications. And now we start discussing about the next kid on the block, which is unrestricted file upload. This is again a variant of these lines of attack we consider. And the key idea of unrestricted file upload, UFU for short, is that uploaded files represent a very significant risk to web application. In particular, if the attacker is able to upload code on the web server, the attacker only needs to find a way to get the malicious code executed. However, it's worth mentioning that unrestricted file upload is not necessarily dangerous just because the attacker uploads executable file, for instance, in the form of PHP on the server, but it might be surprising that many files are actually dangerous. If the attacker is able to inject HTML on the server, for instance, this unrestricted file upload vulnerability will become an enabler for stored XSS. If the attacker is able to send HTML to the server, since this HTML can include script tags, which are under the control of the attacker, this HTML can be used as a vector for persistent XSS on the machine. Also, there are other files which look innocuous but are not innocuous at all, like the SVG image format is very dangerous, because if you check into the SVG specification, you will realize that you can embed inline JavaScript inside SVG. So by using SVG, you can try to mount XSS attacks against the application. So in general, what we would like to do? What we would like to do is checking the file types which are sent to our server and only allow benign file types to be uploaded on the server. But this is much easier said than done. In particular, if you think carefully, how can we realize what is the real file type to implement, for instance, a blacklisting procedure? This is not obvious, right? We have many different ways to try to look into file types. Let's see a very funny example. This is something you can experiment on your Linux system. I will execute it now online for you, so I hope it works, because most demos don't work when you try to supposed to do it, but let's hope it works. So I show you this kind of attack. This attack is called a GFAR attack. What is a GFAR attack? We have here, in this directory, I hope you can see, we have a GIF file, which is I, and we have a jar file, which is called Sky. So a GIF file is just an image, right? And since it is an image, it is benign. Here we have a jar file. You might know that a jar file is some executable file in general. It's some Java file which you can execute on the machine. Now let's make this fancy experiment. So we pick i.gif, we pick sky.jar, and we concatenate the content inside a file which we call gfar. Okay? So I created a new file which is called gfar, and the extension of this file is GIF. Question is, which kind of file is that? This is quite funny. Since we don't know what is the right file, it has a GIF extension, so it looks like a valid image. But of course, I can just change the extension arbitrarily as I like. So I cannot just trust the extension of the file. So since I don't trust the extension of the file, I will use the file utility to learn about the file of this guy. So let's call the file utility over gfar.gif. And this is what the file utility is telling me. This is a GIF image data. Okay. This is an image file. So since it is an image file, I'm not supposed to unzip the image file. What's happening? You can see, if I run ls, a new file appears into the directory. This new file is called sky.txt. What's in this file? I don't know. Could be a malware. Luckily, it's just a string which I put inside here. And what's happening? What's happening is that according to unzip, this is a valid archive. There is some warning here, but nevertheless, unzip was able to extract the content of the file. So a jar file is essentially a zip file. You can open a jar file using unzip. So what's the bottom line here? The bottom line is that if I trust the file utility, in this case, I will be happy to upload gfar.gif on top of my server, because this is a valid image according to this guy. On the other hand, this is a very dangerous thing in principle, because if the attacker is able to unzip file on the machine, the attacker might be able to indeed extract the attack payload from here. So what's happening? Why does it work? The explanation is the following. GIF images bring information about the file format in the first bytes of the file. So they have a sort of a header which is telling that this is a GIF image. The file utility implements some kind of sophisticated heuristic to try to infer the right file type. I'm not going to cover the heuristic in detail, but what I want to mention is that the information which is privileged is exactly the information which is in the header if this information is present. What is interesting is that jar archives, which are essentially zip archives, carry information about the file format not in the first byte, but in the very last byte. So when you call the unzip command is aware that it is supposed to operate on zip files, so the information about the right format will be checked in the last byte. The extra bytes at the beginning of the file are discarded by unzip. You can see that here, by this warning, the warning is telling you that there are some extra bytes at the beginning of the zip file, but nevertheless, and zip will be able to try to process the file anyway. And so by discarding this extra byte, the content of the zip file will be correctly extracted. So this is raising an interesting point. Checking the right content of the file is not trivial, because even you cannot essentially trust the extension, right? This is obvious for any computer scientist. But at the same time, even checking the content on the file is not sufficient, because file is indeed checking the content of the file, and nevertheless, file is still fooled by the GFAR attack. I show you here an example of a real-world vulnerability which affected a popular plugin for WordPress in 2011. This vulnerability is a combination of an unrestricted file upload vulnerability, so an UFO vulnerability, and a remote file inclusion vulnerability. How does the attack against this TimThumb work? The idea of this plugin is that it is an image resizing plugin for WordPress, and the key functionality of the plugin was to creating some thumbnails of images which were supposed to be stored on trusted third-party sites. So the idea is you can pass to this plugin a URL pointing to an image file on a trusted third party. And what the plugin will do is getting the image, store it, cache it in a public directory, and producing a thumbnail. So essentially, in this case, we have potentially a way to let the attacker inject content inside the application through this WordPress plugin. To understand the details, let's have a look at the intended usage of the plugin. The plugin is very simple. You just call timthumb.php, and you pass as a parameter a source parameter containing a link to a trusted server, and in particular, you want to load an image from this trusted server. To prevent abuses, what TimThumb was doing was checking the host name here against a whitelist. But since the implementation of the whitelist was a bit sloppy, the attacker was able to try to abuse this functionality to load an arbitrary PHP shell in the public directory. So the key idea of the attack is that the attacker, for instance, sitting at evil.com, generates a subdomain, say trusted.com, which is essentially one of the subdomain which is allowed by the whitelisting policy of TimThumb. So in particular, since the checking of the whitelist was just merely checking for the inclusion of the string inside this parameter, by creating a fake subdomain, we're able to fool the verification process. So in particular, the attacker can pass as a parameter a shell script which is hosted on the attacker control server sitting on a maliciously crafted subdomain. And by doing that, what TimThumb will do is fetching the shell.php file, store it, and cache it in a public directory. So since this directory is public, what the attacker can do is just pointing the browser to that public directory, and from there, the attacker will be able to execute arbitrary code. This vulnerability was affecting a WordPress plugin. Of course, you can imagine all the consequences of this kind of attack. So how do we prevent it? In general, I would like to tell you that unrestricted file upload is a very complicated vulnerability to deal with. There is a very recent paper published at this edition of NDSS this year, where some researchers for Korea presented a tool to automatically look for UFOs vulnerabilities, and they found that they are indeed extremely pervasive in the wild. I try to give you some idea on why it is complicated to prevent unrestricted file upload. In particular, first advice, you have to sanitize the content of the file name. If you don't do that, you have a problem of integrity. We discussed that when we analyzed path traversal. Let me move back. This example, essentially, this is combining a path traversal with an unrestricted file upload vulnerability. And you can see that if you don't sanitize the name of the file, you might eventually completely break the web application logic. So for integrity reason, it is important that you sanitize the name of the file. How do we sanitize the name of the file? We already said that we can use canonicalization to bring the file name into a simple format to parse, and then we check appropriate conditions over the canonical representation of the file name. Second point to mention is that we said that file extensions cannot be trusted. This is obvious, okay? Nevertheless, it is still useful to whitelist file extension. The reason is that it's not that we can trust that file extension, but the reason is that there are some programs which require specific extension of files. So if you try to run the program over a file with a wrong extension, the program will not run. So by limiting a little bit the extensions which are allowed on your server, you're also limiting a little bit what the attacker can do. So preventing some extension is not like a panacea, but nevertheless, it's useful because it's a mitigation technique. Also, I wanted to point out that the browser is kind enough to provide the web server with an header which is called content type, which contains the intended content type of the file. This information is useless. You cannot trust it because since it is generated by the browser, it is forgeable. So if the attacker runs a modified browser, the attacker can also change the logic of the population of the content type header so that the content of the content type header is not trusted at all. Other interesting point to mention is that it's not important to check just the extension of the file. It's very important to check also the content of the uploaded file. In particular, we said that checking the content of the file is not necessarily easy. We said, for instance, that if you call the file utility, which is a very popular way to check the right type of the file, you might be fooled because that utility is not bulletproof. Of course, you have to implement appropriate recipes to sanitize the content, but I really want to mention also the possibility of re-encoding the content. What do I mean by re-encoding? What I mean is that, for instance, let's assume you want to let the attacker, let your users upload images on the file on the site. If the user uploads an SVG image, what you do is that rather than storing the image directly, you process the image using some image processing library, and you save the content after processing. So for instance, you pick the SVG image and you convert it into a PNG. That could be an option. This idea of re-encoding stuff is done, for instance, in the case of YouTube. In YouTube, you can upload arbitrary content, right, from your machine, but the content you put is not really saved as it is just rather re-encoded, both for performance and for security reasons. Another useful advice to prevent UFO vulnerability is to restrict upload operation to authenticated users. Why is that? This is a mitigation, of course, especially if the attacker is able to create a free account. But nevertheless, you're making the life of the attacker more complicated because it means that you're forcing users to create account, which is something which is hard to automate in general. And also you might spot that some authenticated user is doing something stupid and ban the account if you realize that the user is trying to exploit some vulnerability. Other very important advice is that the uploaded files should not be easily accessible by the attacker. In general, a good advice is to put these uploaded files out of the web root. What is the web root? It's the part of the file system which is indexed by the web server. If you put the uploaded files out of the web root, it means in particular that if the attacker is able to upload a PHP shell, the attacker will not be able to access the content of the shell. So this is already a very good mitigation technique. Even better, you might consider the possibility of hosting these files over an external domain. Why this is useful? This is useful because by putting something over an external domain, you are essentially separating origins. And if you put this information on an external domain, it means that if the attacker is able to upload, for instance, HTML over an external domain, this XHTML could be used to run XSS, but that XSS will be confined to an external domain. So you're mitigating a lot the dangers which are enabled by the possibility of uploading files. If you're curious about this, try to have a look into your Facebook profile and have a look where your profile picture is saved. You will realize that the profile picture is not saved on facebook.com, but it is saved over the Facebook CDN. And this is exactly to prevent this kind of dangerous vulnerability. Last point which I want to mention, it is very important to put limits on the file size to avoid denial of service attack. If you let the attacker upload files which are too big, you might exhaust the memory of the server, while if you let the attacker upload files which are too small, you might let the attacker create so many files that you are essentially creating a bunch of troubles in terms of denial of service. So again, this is a complicated vulnerability to deal with. Probably we don't have any perfect recipe to prevent all the possible attacks, but we have tons of ways to mitigate the danger of unrestricted file upload. So this is basically it. I leave you a few minutes for questions if you have some.